Hello everyone. Today I want to talk briefly about the reverse bias operation of a diode. We're not going to spend too much time on talking about it kind of in the normal area of operation because it's not that interesting. We've already concluded that we can essentially just assume that in reverse bias that the only current that is conducted is that saturation current, which is quite small, right? And we can attribute that very small current to the fact that with reverse bias applied, this effective voltage across the depletion region in fact increases. Okay, so where with forward bias we said we get an effective decrease in the that built-in junction potential, here we get an effective increase. And we'll talk a little bit when we get into BJTs or bipolar junction transistors that we in fact get an effective widening of the depletion region. Okay, so due to that increase in effective junction potential, the diffusion component of the current that was under zero bias is exactly equal to our drift current. This diffusion current becomes nearly negligible. Okay, so our diffusion currents of our majority carriers can pretty well be ignored, and our reverse current is therefore entirely or nearly entirely due to drift current. Okay, so and this drift current is very small. Okay, and in fact we can look at this a little bit further if we want to look at how the carrier concentration is impacted by this increase in effective junction potential. And if we revisit our expression for what the concentration of minority carriers is at, well, in this case at the edge of the depletion region in the N-type material, we can show that with increases in this reverse voltage, and again remembering that this is what we're calling V naught in our, so this is V naught, the built-in junction potential, but this equation is such that it's going to tend to result in a minority carrier concentration that's nearly zero as we increase the reverse bias. Okay, so our diffusion current is much less than the zero bias case, and our current in general, due to this minority carrier injection, is reduced, and due to this reduction in our concentration of minority carriers. Okay, so all that to say that our operation in reverse bias, not super interesting. It's small and primarily based on our saturation current, and we looked at that it's very temperature dependent, but other than that, not super interesting. What I want to spend a little bit of time on is talking about what happens when we get a high enough reverse voltage to cause reverse breakdown. Okay, so in a real diode, we have So let's say in a real diode, a new region that our diode equation doesn't really represent is defined, and this region is known as the reverse breakdown region. Okay, and if we look at what the IV characteristic for our diode looks like when we account for this reverse breakdown region, we see that for large enough values of reverse voltage, the diode in fact does start to conduct again. Right, so we see that here. So this is this reverse breakdown region. So if the diode voltage is increased far enough, let's say in the reverse bias, current eventually flows. Okay. This is known as junction breakdown, and the name breakdown kind of suggests that it's a catastrophic event, but in fact this is non-destructive. It does not destroy the diode as long as that reverse current is controlled to be within the power limits of the diode. Okay, the reason for the breakdown is rather interesting. So if we look into the mechanism that causes this breakdown, there's two primary phenomena at play depending on the voltage levels that cause the breakdown. Okay, and those two mechanisms are referred to as Zener breakdown or avalanche breakdown. Okay, and the voltage at which this breakdown occurs is one of the determining factors on which mechanism is at play here. So the voltage at which the breakdown occurs, and this leads to a little bit of confusion, because often we refer to the breakdown voltage as the Zener voltage. So as shown on our plot here above, called VBR, but it's also referred to as VZK. You'll sometimes see used, and the ZK refers to Zener knee, so kind of that knee on the curve here, and hence the name Zener knee, or V subscript ZK. Okay, but just because it may be labeled ZK does not mean that it's necessarily due to the Zener effect, and we're going to look at what the difference between the Zener breakdown and avalanche breakdown is here in a second. Okay, so I said that the mechanism for breakdown is dependent on the voltage, and generally if the breakdown occurs below 5 volts, then the phenomena is usually due to Zener breakdown. And again, I'll define what Zener breakdown is here in a little bit more detail in a second. While if the breakdown voltage is greater than 7 volts, the breakdown is attributed to avalanche effect. And you're thinking, well, what about between 5 and 7 volts? It's not entirely clear whether it'll be Zener or avalanche, or possibly a combination of the two. But for the most part, we can assume if it's under 5 volts, it's Zener breakdown, and if it's over 7, it's primarily avalanche breakdown. So what is that mechanism that we're calling Zener and avalanche? Zener breakdown is a result of the E field that's established due to that ever increasing voltage across the depletion region. That E field gets high enough, it will break bonds in the lattice structure of our atoms and cause the our charge carriers to be pulled across our depletion region. Okay, so if we go back to look at our maybe this form of the equation again, if this reverse voltage here gets high enough to cause a strong enough E field, right? So remember, our E field is a built-in junction potential due to this junction potential like this. So if this E field here gets sufficiently strong, it's going to start to rip, in this case, holes out of the lattice structure and pull them across the depletion region, or electrons get ripped out of the lattice structure. Maybe I should show electrons with this, another color. Those electrons will get ripped across this depletion region, and that's the Zener effect. Okay, again, due to a high E field here. whereas the avalanche effect is a little different. Still result is initiated from a high E field, but this high E field accelerates the movement of these minority carriers across our depletion region with such force that will have our bonds in our lattice structure become broken by collisions. And you can kind of picture that avalanche effect, right? We have these minority carriers accelerating through our semiconductor, and that high acceleration causing them to collide with other charge carriers, breaking them free, and we get this snowball effect or avalanche effect. Okay, so generally for kind of a general purpose diode, the location of this breakdown voltage or this knee or breakdown voltage is quite a large voltage, and often in the hundreds of volts, and you can look at data sheets to see what that might be. For example, if we look at diodes that were used in our lab, here's one of the diodes that we used in the last lab. If we scroll down here and have a look, we'll see that peak repetitive reverse voltage, working peak reverse voltage, DC blocking voltage, and they have some different names for it. This one's not really high, depending on the series of diode, 20 volts, 30 volts, or 40 volts. If we look at the other rectifier diode that was used in the lab, so this one was a Schottky diode, and I'm not sure if anybody picked out that it was a Schottky diode, a special type of diode that has a low forward voltage drop, lower than your typical silicon diode. Although this is silicon, but it's manufactured to have a lower voltage drop, and we see that it's in general lower than a typical diode. Whereas this kind of very characteristic silicon diode has a forward voltage drop that is kind of more typical of what we expect. I guess this is showing a maximum forward voltage drop of 1 volt. That's for high levels of current. Anyway, what we're interested in this case is these reverse current, so maximum recurrent peak reverse voltage. And again, this is without breakdown, so we see the 4001 is 50 volts all the way up to 1000 volts for the 1M4007, and you note now that is the primary difference between these different series of diodes, is that reverse breakdown voltage. Okay, but there are diodes that are specifically designed to operate in reverse breakdown, and those diodes are referred to as Zener diodes. And the name suggests that all of these diodes are a result of our Zener effect, but in fact they're not limited to the Zener mechanism. Okay, so the mechanism of breakdown in a Zener diode. May or may not be due to the Zener phenomenon. Oops. So again, the name is generic for all diodes that are meant to operate in the reverse breakdown, but again, it doesn't necessarily mean that they are purely due to Zener breakdown. They may in fact be avalanche, and again, telltale sign is kind of where that breakdown voltage is specified for a particular diode. So if we go back here and look at some Zener diodes, here's a series of Zener diodes, and we'll see over here in the columns on the left that you can get them for kind of any breakdown voltage that you choose. These ones go up to 56 volts of reverse breakdown for typical values, right? So now this is at a specific current, so at this particular current there is some variation in exactly where it breaks down, because, well, if we go and back and look at the curve here, this is a rounded edge, so it's going to be dependent on current on where we fall in terms of reverse breakdown voltage. So bias does have some effect, and there is, it's not maybe clear here, but there is some slope here. The slope is not in fact infinite, although it might appear that way in this diagram. Okay, so just to go back to those data sheets here again, here's a couple of examples of series of Zener diodes, and when you look at the diode themselves, physically they don't look any different. Okay, they look essentially exactly like a standard diode package. Again, here's just another family with available in a variety of breakdown voltages. This one only going up to 12 volts. Okay, so in a schematic symbol, the Zener diode, oops, let me make this more clear. The Zener diode is depicted by having the little kind of wings on the cathode marker. Okay, so although on the schematic it is depicted differently, there's no difference in physical appearance. And in the forward direction, the Zener diode is going to act much like a standard diode would act, but they're not. You're not typically using a Zener diode to operate in the forward direction, although it can. I want to talk just briefly about one of a kind of a common application for a Zener diode is to use it as voltage regulation. And we often don't use kind of a discrete Zener diode to do this. It's Zener diodes often integrated into our devices or voltage references to perform this voltage regulation, and so we wouldn't pick our Zener diode and typically create a voltage regulator with a Zener diode directly, because the operation is going to be, the operating point is impacted by how it's biased in that, so those things are often controlled in an integrated circuit. Okay, so Zener diodes are often used to regulate a voltage in the circuit. Again, although they might be used, they're often integrated, and I'm not suggesting you go and buy a Zener diode to perform regulation. Get a device like a regulator or voltage reference, depending on what your application is. Okay, so let me just skip that statement here. Let's so we've back a little while ago we talked about a voltage divider, and if that voltage divider were to be built purely from resistors to generate a specific voltage, you know, maybe 2.5 volts, that voltage divider is impacted by having a load on it. So to maintain voltage of 2.5 volts at the midpoint of this voltage divider, it's really important that we don't draw any current from the center point, right? And we can do this by using our unity gain buffer that we discovered back in our op-amp section of the course, right? So here we get a nice reference voltage of 2.5 volts, and it's independent of what load might be connected out here, right? This load could be variable, and my voltage reference, assuming a rather ideal op-amp, this reference voltage will remain at 2.5 volts. Okay, so it seems okay, but you might note in looking at how this reference voltage is arrived at that it's a function of my resistive voltage divider at the input of that op-amp times my supply voltage, right? And this gives me 2.5 volts. But note that this is highly dependent on my supply voltage. So what if my supply voltage isn't stable? Right? Which is often the case. The supply voltage might fluctuate, or maybe we're generating a supply from maybe an AC source, so maybe there's a lot of fluctuation. So in fact, if supply voltage increases by even 10%, so does my reference voltage. Right? So if my maybe my supply voltage is coming from a battery, as my battery drains, then my supply voltage is going to reduce, and my reference voltage is going to be impacted as well. So that doesn't seem like a good scenario, right? So we need something better. We need to regulate the reference voltage and reduce its dependence on the supply voltage. Okay, so well, we've just talked about Zener. Seems like an obvious choice. So let's take and bias a Zener diode in the reverse direction. Okay, and let's assume this Zener diode has a reverse breakdown voltage of 2.5 volts. Okay, and we need this resistor in here to act as a current limiting resistor. Otherwise, this if the 5 volt were applied directly to the Zener diode, then we're going to get massive amounts of current, and we're probably going to fry our Zener diode. Okay, and let's define some current here, ID. Okay, and it's important to maintain the current through this Zener diode at some fixed level, such that we don't change where it is on the operating curve. Okay, so if I let me exaggerate this slope here a little bit. If I want to maintain my operating point at some spot so that my voltage stays fixed, I don't want my current through my diode fluctuating so that my reverse breakdown voltage is fluctuating here. Okay, so in that way, it's still going to be beneficial to have some kind of a buffering circuit to isolate the biased Zener diode sorry, bumped my power button there, to bias that Zener diode to be at a specific operating point. Okay, so even as it stands, the Zener diode is going to be impacted a little bit, and its operating point is going to be impacted a bit as you know, the power supply voltage changes as we stated. So if I just show kind of a chunk of my IV curve here and show that my Zener diode is going to look something like this, and if we assume that this Zener diode has a breakdown of 2.5 volts, minus 2.5 volts, I guess, we can look at where we're operating on that curve for different supply voltages, and I'm going to call this V rail, as we often call our supply voltage our rail voltage. So V rail, if it's 5 volts, then my current through my diode is going to be 5 volts minus 2.5 volts, the Zener breakdown voltage, divided by R, and I'm going to be operating at about reverse current of 2.5 milliamps. Okay, so that let's say puts me down here somewhere on my breakdown characteristic. Okay, if V rail drops to 5 volts, or sorry, 4 volts, my diode current is my supply is now 4 volts, so my diode current, of course, is impacted. This, remember, was 1K, and I now have a diode current of 1.5 milliamps. Okay, so with drop in voltage, I do move up my operating curve here slightly, and yes, there is going to be some change in voltage here between these 2 points, but we'll note that it's very small. Okay, so this delta V here is approximately equal to 0. So my impact is that I have a constant reference voltage being generated independent of the fluctuations in my power supply voltage or my rail voltage. The other thing we should be thinking about in choosing our diodes here is the power. So that Zener diode is dropping 2.5 volts, and its current is 2.5 milliamps. So here where the diode needs to dissipate 6.25 milliwatts, whereas in this case the Zener diode is dissipating 3.75 milliwatts. So just something to note in choosing your diode, to make sure it's rated for the appropriate power rating as well. Okay, this power calculation here is simply my breakdown voltage of my Zener times my current through that Zener. Okay, and of course, as noted from these power calculations, the larger the difference between the unregulated voltage, which we call V rail, and the regulated voltage, which is the breakdown voltage of the Zener, the higher the power dissipation. Okay, so just to look at an interesting application of Zener diodes and the reasoning why they're often used in voltage regulation or voltage reference applications, because small fluctuations in the operating point due to changes in current will have very little impact on the voltage across that Zener diode, and the impact of or the magnitude of that difference is a function of the slope of this characteristic. Okay, so we generally want to make sure we're biasing these diodes in a steep region of the characteristic. We want to stay away from this region because small changes in current can have a more impactful effect on the voltage across the diode in that region. So we want to be well into the breakdown region while still having reasonable levels of current.